and then I will allow people to ask you questions directly, I guess, or even myself, I can translate the questions that are posed by the rest of the attendants. Okay.
Okay. So I will then I share my screen here. I hope it works. Can you confirm it works? Can you see my screen? Let's see. Oh yeah, okay, yes. Some of you are saying yes in the chat. So okay, so then I will talk about optical excitations with free electrons, and then I'm going to try to focus on the quantum aspects of this interaction. And then a lot of things have been happening over the last decades with free electrons, and that's what I'm going to try to focus on. So first of all, this is an old graph already that summarizes the main techniques that are used to resolve optical excitations in space and energy, so to do a spectral microscopy. And basically, what we have here is a clear difference between the electron wavelength and the photon wavelength at the typical excitation energies that we are interested in. And then this difference, actually what it makes is that the electrons, it renders them particularly useful to have a good combination of a spatial resolution and energy resolution, right? So electron energy loss spectroscopy, cathodoluminescence, beam, etc. Those are among the best techniques to resolve optical excitations in nanomaterials. Compared to other optical techniques, including near-field scanning optical microscopy. So lots of things have happened over the last 10 years or so, and among them is the possibility of having a temporal resolution in the electrons. And then now some of these techniques can operate with resolutions ranging from the nanosecond to the femtosecond. I will show you some examples. And the prospects are that the attosecond will be reached very soon, as you will see. So first of all, I will just summarize some important or relevant results in the area. So what electrons are capable of doing. So with electrons, this is already a relatively old work. So they were able to resolve through the deflection of electrons and the energy loss of electrons transmitted through thin foils, the dispersion relation of plasmons that are hybridized between the two sides of a thin film, right? So it's a beautiful demonstration and direct measurement of this hybridization of the plasmons. Later on, people were looking into low energy plasmons when the electron microscopes advanced to have better and better energy resolution. For example, in this case, it's just the silver nanowires, where you can see a standing plasmon waves. This is an example of a recent work in which we have collaborated together with the group of Mathieu Kosiak in Orsay, where we are looking at very long copper nanowires. And then you can see tons of plasmons that are confined, the standing waves in these wires, with very high quality factor, surprisingly, despite being copper, and down to very low energies, thanks to the new capabilities of these microscopes. That's when you look at the electron energy loss spectroscopy, but also the electrons are producing luminescence. So this is the cathodoluminescence emission. And when you resolve in space through the position of the electron and in energy by performing a spectroscopy on the emitting light, then people have been looking, for example, in this case, topological features in two-dimensional photonic crystals. This is another work in which we have participated with the production of chiral light from bombarded silicon spheres. Then the spherical symmetry of the sphere is broken by the position of the electron beam, also by the direction in which the light is emitted, and then you produce controllable chirality in the emitted light. Also, these are plasmon waves that are supported by circular groove in a cold crystal, also resolved through catoluminescence. And the last technique I want to mention is PNEM, which is photon-induced near-field electron microscopy. So electrons are exposed to the near field of illuminated samples, and this has been used in this example in the group of Kaminer to map photonic bands and photonic states in two-dimensional photonic crystals. Also in the group of Fabrizio Carboni here to demonstrate mid-electron volt energy resolution, just inheriting the resolution by which the light can be controlled, the illuminating light, and this allows us to just look at for example, plasmon standing waves with that kind of energy resolution, right? The advance in electron microscopy and the control of free electrons and analysis of free electrons is so large that you can go to study mid-infrared excitations in the few milli-electron volt region. In this example is just phonons in lithium fluoride. This is a relatively old example of phonons in lithium fluoride in which there is no spatial resolution, so it's only energy resolution here. You can see energy losses produced by electrons that have generated phonons in lithium fluoride, but also energy gains. And these are coming from electrons that are gaining energy from phonons that are already excited. At these energies, phonons can be thermally populated. So the electrons can pick up some phonons and get accelerated, and that's energy gain, the energy gain side of the spectrum. Now, the ratio between gain and losses, it tells you what is the temperature in the sample. And this is something that can be done now, like in this example from Batson's group, with nanometer resolution in state-of-the-art electron microscope. So you can determine the temperature by comparing gains and losses as a function of the position of the electron beam. This is another example yet of how the technique has advanced. So this study by Quentin Ramasi, so it combines atomic spatial resolution with mid-electron volt energy resolution, and to map phonons and the phononic density of states in a graphene lattice with a silicon atomic impurity, right? So they were able to basically determine how differently the atoms are vibrating near the silicon. In this other work, in which we collaborated with the group of Mathieu Kosiak, we were looking into a strong coupling of plasmons in long silver wires that are coupled to bornite-right phonons, and you can see a signature of strong coupling depending on the characteristics, in this case, of the nanowires. And another example here is just mapping the phononic bands of graphite or bornite-right just with electrons. Okay, so I think this gives you more or less a panorama of the things that can be done regarding the study of optical excitations using free electrons in electron microscopes. Now to the basics. And then if you have an electron moving with a certain velocity v here, then the electromagnetic field carried by the electron, which is evanescent, is just if you see it in the rest frame of the electron, is just 1/r potential. But as it moves, then the electron creates a field that is rising and then decreasing as the electron leaves the sample region. And you can decompose this in different frequency components. And each of these frequency components, it has an evanescent decay away from the electron trajectory with the characteristic distance, which is the velocity divided by the frequency, okay? In more detail, you can actually solve this analytically. So the electric field produced by the electron, decomposed in different frequencies, is just a combination of these exponentially decaying Bessel functions, modified Bessel functions. You can see here how the electric field and magnetic field components decay away from the electron trajectory as a function of this distance r. So you can see that here. Okay, this is the basics for studying the interaction of electrons and samples. and to basically calculate what are the spectra, the inelastic spectra produced in the electrons. So you have an electron that supplies a certain external field, again resolved in frequency, and this will produce a scattering of this field in the far field. That's, for example, emission in the case of catoluminescence. In principle, at different frequencies, so each of the frequency dependence is contained here, right? So how do you treat this problem? So you can use a very simple approach, which consists in describing the sample with a frequency-dependent electric function, depending also on position. In a more sophisticated model, you can do ab initio, and in general have the electric function that is non-local, depending on r prime. But what you have is an external source. So this external field of the electron created by this classical charge. Again, this classical charge is decomposed in frequency components. And then you solve Maxwell's equations, which is this summarized here. As a function of the current, you just resolve for the electric field created by the electron. The electric field in the far field is the catoluminescence, is the amplitude, the emission amplitude. And then what you can do is from this emission amplitude, you integrate the Poynting vector associated with it over a distant sphere. And then that gives you integrated also over the time. And this gives you the energy that is emanating from the system at a given frequency. Now you divide by h bar omega, the photon energy, that's the number of photons, right? And this semi-classical prescription by which you introduce a quantum effect here, by just saying the emission consists of photons. In a detector is actually photon count, so the detector knows already that. So this gives you the correct result if you compare with the fully quantum mechanical treatment of the problem, and that's the photon emission probability, right? Now, you can use optical methods to do essentially a similar thing, just illuminate with light, look at the far field, scattering. Again, you have the response of the sample, and then you solve Maxwell's equations and you have the scattered field. No? What happens then when you combine the two of them? So you have an external field that is the light plus the electron, and then you have a scattering of the light plus emission, catoluminescence from the emission from the electron. And then all of this, in principle, could interfere in the far field. And a way of treating this, you have an electron that is a point charge. So the classical electron for now is, again, you have a certain current. You have also the external field of the light. You solve your Maxwell's equations, and you end up with the photon emission probability as a function of the frequency, also as a function of the direction of emission. That involves the coherent superposition of the scattering amplitudes associated with the scattering of light and also with the catoluminescence emission by the electron. Okay, so that's this expression. But where is the electron during each optical period of the light? So typically, an electron is not going to be a point charge. It's going to be, it's going to have a wave function that can extend over maybe hundreds of femtoseconds, or even more. Whereas the light consists of optical cycles, typically for 1 eV. These optical cycles last for 4 femtoseconds each. So the wave function of the electron, this gives you the distribution of where the electron is, but then you don't know where the electron is. There is an uncertainty, and therefore it's not clear that this interference must be maintained like this. Okay. Now, through a very long process that involves this, or we use this macroscopic QED, quantum electrodynamic formalism, that has become very popular recently in the description of quantum process in the presence of macroscopic media. So we were able to solve the problem. So basically the solution is that you have to integrate over the electron wave function, and at the same time also add some extra terms that come from a pure quantum mechanical origin. Now you can actually condense some of these integrals when you do a little bit of math, just this integral together with this phase, etc. No? You can wrap it up in terms of this parameter, which is nothing but the Fourier transform of the electron wave function. So your emission is now your far field emission, combination of the light and the electron is now depending on this integral that we call coherence factor. You can see in the case of the point particle, where the wave function is just the delta function, the square of the wave function. So this becomes m becomes 1. So this factor completely disappears and we recover the classical limit. When the electron is distributed, then this is not 1. It's in general less than 1. And then you have some depletion of the interference between the light and the cut luminescence. Okay, so how can this be done? I mean, we are talking about electron pulses. Maybe you have light in order for them to coincide. Maybe you have also to have light pulses. Well, this is done in the context of PINEM, so photon-induced near-field electron microscopy, in which you illuminate in a microscope on the source, the tip that produces the electron source, you illuminate with the laser pulse that produces the electrons, and then you have the electrons are focused to the sample, and then part of the laser is just now diverted to the sample, and so you have a sample that is illuminated by both electrons and laser pulses of femtosecond duration. So this was a technique that was pioneered by the late Ahmed Zevail. So he won the Nobel Prize in femtochemistry, and he actually wanted to get a second Nobel Prize. Actually, he said the statistics were in his favor. You have one, then it's more likely to have another one. So what he did was to invent this technique whereby he was able to have femtosecond pulses of electrons and light interacting with the sample, and as a result of that, then the electron could absorb or emit multiple photons, because the interaction could be really, really strong. You know, with femtosecond pulses, you can crank up the intensity without damaging the material. That's one of the advantages. So this is the first spectrum they published in this context for this technique, PINEM. So that's the zero-loss peak of the electron, so the instant electron, and then you can see in various peaks here associated with the emission of photons by the electron. It's actually a stimulated emission because the photon emits into the light field coming from the laser. Or for the same, then this you have a stimulated gain, so the electron can pick up photons from the laser field and also undergo energy gains. This spectrum is typically symmetric because of the nature of this gain and loss processes. We predicted at the time that if you crank up the intensity of the light, eventually the spectrum, so here is just each horizontal line is just a spectrum. So, and then the scale in the spectrum is just in terms of the photon energy. So number of photons that are emitted by the electron or absorbed by the electron. So eventually you have some kind of quantum billiard physics where multiple peaks, multiple photons are just, going between different channels. So basically multiple photon exchanges occur during the interaction of the electron with the sample. Actually, this interaction takes place in a sub-femtosecond scale, so this is really ultra-fast physics. This was demonstrated a few years later in the group of Klaus Roppers, who basically looked at the energy loss spectra as a function of the light intensity, and then he saw this evidence of quantum billiard physics. One of the most important consequences of this is that you have an electron that contains components which are coherent if your external light is coherent with different energies. No, if the electron has absorbed photons or emitted photons, so you have electrons that are accelerated, components that are accelerated, or components that are decelerated. As a result of that, after you propagate the electron for a long time, then there will be compression of the electron, and this is actually what you find here illustrated. So you have the electron, you undergo Pinem interaction, so the electron picks up energy components components with higher energy and lower energy. Those evolve with different velocities. Eventually, is in the same wave function, coherent wave function, the electron develops temporal dependence, and what happens is that at a certain optimum distance, there is compression of the electron wave function, and then it consists of a train of pulses, each of them of a duration that is much less than the optical period. For example, for 1 eV light, that would be much less than 4 femtoseconds. And then the distance between them is the optical period, 4 femtoseconds. Now, by now, Pinem is a well-developed technique. So people have been using this method, as I said earlier, to map photonic crystals, to produce up to hundreds of photon exchanges between the electron and the laser field under resonant conditions. People have looked into this compression of the wave function. These are experiments showing attosecond compression. So this train of pulses, each of them can have even down to an attosecond duration, right? So we are back to this scheme where we have the electron wave packet, maybe a light pulse, the two of them interacting at the sample with this type of description where we have some coherence factor depending on the wave function of the electron. Now, if we used electrons that are modulated using Pinem, like this, then there is a well-established procedure to obtain this coherence factor. The details you can see here, they are semi-analytical. And then the result is that as a function of the light intensity, so basically where you are in this ladder, up or down, more intensity, less intensity, as a function of this parameter, also as a function of the propagation distance, which typically is in the range of millimeters, then you have a coherence factor that can be in this range, okay? So, so you have these modulations, but what you see is, first of all, it's always smaller than 1, so you never get with this Pinem the perfect classical electron behavior, but still you get something that works towards the classical behavior. And what we illustrate here is a cathodoluminescent spectrum calculated for an electron passing near a certain particle. So that's this smooth curve. And now that's for an electron that has not been modulated with light. But if you use modulation with light in these resonant conditions, then you will have these dips in the spectrum that reflect this quantum aspects, I mean, from the wave function of the electron. No? Okay, so actually you can play with the delay between the laser pulse and the electron pulse, and for example, look at the electron gain or loss of energy, and this is represented in this panel, but also how much radiation is emitted, represented in this panel. So these are units of the optical cycle of the illuminated of the modulated light, modulating light. And then you have different channels of energy to go, as I said, towards the detector as energy change in the electron, also decay, inelastic decay inside the atom, or also stimulated processes that go end up being changing the energy of the incident laser pulse, right? All of them sum up to 0 because energy is conserved, but you see some dependence on the delay between these two electron and laser probe. This is a study we've been looking at here in which instead of using laser light, so far I've been telling you this is using laser light, and also here typically you use the laser to produce this modulation. A laser has a certain coherence properties, so these are coherent states, But you can use also quantum light or for example, phase squeezed or amplitude squeezed light, and then these characteristics of this coherence factor will be totally different. Okay, so you can in principle manipulate this quantumness of the electron pulses depending on the type of light that you are using. As a different but related proposal, we just speculated that the cathodoluminescence emitted, for example, into a waveguide by the electron should interfere with the laser that is modulating the electron. So the end result is that you have some correlation in the statistics of the electron, the photon emission. And then you can, what the bottom line here is that you have transfer of coherence between a laser light and another system where the light is collected, mediated by free electron, okay? Which is, I think, quite spectacular in itself. So we can have also multiple electrons. What happens if you have more than one electron? Now we know that electrons have certain coherence properties depending on this coherence factor. If they are not totally point particles. If they were point particles, the coherence would be perfect. It's just the classical solution of Maxwell's equations. Because they are not, and they have quantum nature, this coherence is lost partially. But then the full solution for this system, for when you have light, electrons, everything, then you have a contribution to the far field radiation or far field photon count, which is the cathodoluminescence emission from the electrons, like independent electrons, some for electrons, light scattering. Then you have electron light interference, similar as before through this coherence factor. Then you also have electron-electron interference, also made by these coherence factors. Okay, you have all of this. Let's just analyze in a more intuitive way with just a simple calculation. So you have one electron interacting with some optical mode, plasmon, something like this. Then you have a spectrum that has a certain peak centered around some excitation energy. Now, what happens if your electron is now modulated in the vertical direction in the form of the shape of two wave packets? Okay, so it's just one electron, only the wave function is modulated in two wave packets. So according to the previous expressions, basically what you have is a total independence of the electron excitation probability. So the excitation probability is going to be basically independent of the wave function, because here you have to do the longitudinal integral of the wave function, which is sums up to 1 because of the normalization condition. If you have, so the emission then, the excitation is totally independent of the shape of the wave function. If you have two electrons, one electron in each wave packet, then things are a little bit different, because then you have interference between them, and that produces a dependence on the distance between the two wave packets. If you have two electrons, but each of them has the wave function distributed in between the two wave packets, then that's yet another different situation in which you have also interference, but with a smaller visibility, right? And the similar conclusions when the two wave packets are laterally displaced relative to the sample. Also, when you produce cathodoluminescence or excitation of a guided mode in this configuration, there should be no dependence on the geometrical parameters of these wave packets when you have one electron. But when you have two electrons, then you have this modulation as a function of this geometrical arrangement. Okay. So this PNM interaction basically telling you that light can be coupled to electrons and change the electrons can absorb or emit photons by coupling to the near field under external illumination. This can be also done in a very, very simple configuration, which is this one. So just a thin film where you reflect light. So a thin film that is totally reflecting not transparent, but that is transparent to the electrons. For example, gold or silver film of a few tens of nanometers in thickness satisfies both of these conditions. And this is what was done here in this experiment. So again, spectra as a function of light intensity, you see this quantum Billiard physics, but also as a function of the tilting angle of just by tilting the plate, you have a very similar effect. Okay, the theory actually works extremely well without fitting parameters because it's relatively simple physics, and there are not many sources of uncertainties in this type of things. So with this type of coupling to this thin film, you have translational invariance in the direction along the film. And then every time the electron picks up one photon and therefore changes energy, so every time you change energy, there has to be also a change in the deflection of the electron, right? Because of the momentum absorbed from the photon. And this is actually something that has been observed in experiments. So there is a correlation between the angle at which the electron is transmitted and the energy the change in its energy. And then both of them are discretized and by the number of photons exchanged during the interaction process. You can also interact with, make changes between electrons and chiral photon fields. In this case, you will create vortex electron beams because you pick up the vorticity from the absorbed or emitted photons. And this is actually something that has been done in experiment. You can see this is experiment here. This vortex beams just by interacting an electron with light, because light has this +1, -1 chiral components, right? So in fact, the modulation of this points out to the modulation of the lateral wave function of the electron, in directions perpendicular to the beam, either here by exchanging linear angular momentum or here by exchanging angular orbital momentum. In general, you can shape your light field to act on a film in which the electron is passing, and by doing that, you can imprint a phase on the electron, and this phase will modulate the entire wave function of the electron. So this is the principle that we have used in this paper to explore the possibility of replacing some of the electron optics components by light. But and then you have, for example, an electron in which you focus the electron microscope in which you focus down to a spot, typically at the position of the sample. That is in the state-of-the-art microscopes. It can be like a sub-angstrom or the other half an angstrom. Then this comes at a very high cost through aberration correction. So these Titan microscopes and the latest Nion, even better microscopes that are now available. Without aberration, then the spot looks very bad. So you don't have the angstrom resolution at all. And then if you want to recover this nice angstrom resolution, one way is by imprinting, as I said, this phase by optical means. So this is something that you can do in principle using a spatial light modulator for the laser light. And this is the result, and there's some realistic conditions that we have explored here, okay? Then you need the electrons to pass through a material, like here or like here, so through a thin film. Although this can create a little bit of a coherence in the electron. So it would be much better to have this phase imprinting totally in Fourier space. And this is something that actually could be done by exploiting this type of physics. This is the Kapitsa-Dirac effect, by which you can deflect electrons just by light without the intervention of any material structure. So I will explain myself. So you have two laser lights, two laser fields that they are counter-propagating, and this is going to create, if the two lasers are coherent with each other, so it's part of the same laser with some mirror or something, then you have a standing wave of light, and this is like an optical grating, okay? What can happen is that the electron picks up one photon and then re-emits this photon. This emission, for example, is stimulated because it goes into the same direction as this laser. And this is, you have a large number of photons coming here, so this can occur with a certain probability, right? As a result of that, the electron experiences a deflection by twice the momentum of the photon, okay? And this can happen a certain number of times. So you will have is just the black peaks of the electron by diffraction in this optical grating. So this was the effect that was predicted by Kapitsa and Dirac in the 90 years ago or so. Of course, at the time they thought that was impossible. There was not even the laser invented, so not possible to get this high intensity. But still, it's difficult, and it took about 70 years to make the experiment and actually observe this diffraction of electrons by light. Now that this can be controlled in a little bit better, than increasingly better. And so what we have done here is just exploiting these latest advances, is just what we propose is the modulation of the electron. So the electron would pass through here by just using a light that is spatially modulated in order to imprint this type of phase and control the electron shape. For example, you might want to have an electron that is focused at the position of the sample with a certain focal shape. This is the transversal wave function, wavelength of the electron, typically in the range of sub-angstrom. Then you need to imprint a certain phase on the electron, the light far field that is then focused on to act on the electron. Because of the diffraction limit, you cannot impose the perfect profile, but it's just limited by diffraction. And eventually you get this type of predicted spot profile. Okay, so I said that I was going to talk about the interaction of electrons with optical modes, but also in the title I said something about challenges and opportunities. No? So I will just discuss very briefly a few of these challenges and opportunities. So this is something that we predicted recently, that due to this spin interaction, if instead of using coherent light from a laser, you just have thermal light, for example, then these quantum billiard structures will look very different. And in fact, you just relate the intensity of the different sidebands corresponding to different net numbers of exchange photons. These ratios between them correlate with the autocorrelation function of order L of illuminating light. Okay. This is actually an experiment that has been recently published in the archive, so this is now being corroborated. We also explored another possibility for using PINEM to investigate the nonlinear response of nanomaterials. It's very difficult. Well, actually, there is no technique now that can render the nonlinear optical response of a nanostructure with nanometer resolution. And this is actually something that could be done with this technique, with this interaction, because when you illuminate the structure with sufficient intensity, you will produce, for example, harmonics, and these harmonics will change the symmetry of the PINEM spectra. You must have seen that all of them are symmetric when you are in the linear regime. In the nonlinear regime, then there is a symmetry in the spectra. And this level of asymmetry gives you direct access into the nonlinear response of the materials. No? Talking about nonlinear response of materials and also free electrons, an electron, if it travels with sufficiently small velocity, the interaction with an optical mode can be very, very strong. And in principle, you can question what is the equivalent fluence if you illuminate with light a certain structure or you illuminate with a single electron. And this is actually, these are the numbers. So the numbers look actually very good for relatively low energy electrons, for example, 25 electron volts. And so that you are completely in the range in which graphene nanostructures will respond non-linearly. So the prediction here is that the single electron should be able to produce a nonlinear response of a material. Actually, these are the calculations, more detailed calculations. We just look at basically the dependence on the spectra, on the polarization, and also on the of the sample, and also on the resulting spectra, depending on the charge, that is the magnitude of the charge. You can have an electron, and then an electron is already producing a substantial deviation, which you normalize to the probe, the charge of the probe, with respect to an artificial electron that has 100 times less charge, right? So that indicates a strong nonlinear effect. No? Electrons have been used also to map photonic structures in the context of scanning time electron microscopy. I think there are opportunities created now by combining this external illumination, like in PNM, with detection of catoluminescence, now extending these free electrons to quasi-free electrons in tunneling electrons, but also in ballistic and field emission from a tip into a sample. Okay, with this, I think I'm giving you a panorama of the different areas in which free electrons and electrons in general are used, how they are used to probe optical excitations. The last example is this proposal in which you have ballistic electrons, so they should behave nearly as free in, for example, in two-dimensional semiconductors. And then with the help of potential gates, electrons could be filtered and then energy analyzed. And then you can also have energy losses similar to yields in electron microscopes, only in a two-dimensional device. And the calculations that you can see in this paper show that the transmission through this device, if you have an area that is decorated with molecules that you want to detect, then this is the current as a function of one of the voltages in the analyzer here. And this correlates very much with the optical cross-section of this molecule here, right? So that's a proposal for a detector, very sensitive detector down to very few number of molecules that should operate under the same principles as electron microscopes, but here there is no light, no photons, just the electron detection. But the principles are exactly the same. And with this, I would like to conclude. So thank you very much for your attention. These are my current members of my group, and I will be happy to answer any questions in this technical system allows us to do that. To the chat. Thank you.
Okay, thank you very much, Javier, for this amazing, beautiful talk. I guess there are many questions. I haven't seen any in the chat. I mean, I will yeah, allow people to talk. Let me open if you raise your hand. I have one question anyway. You say that by interacting with light, you can compress the wave packet of the electron. I guess this can be done for any energy, right? There's no energy or electron energy restriction to that. And then if you can go further, you can make it like a chain of electrons one by compressing wave packets, even at low energies. That would be quite interesting, by the way, in many applications, because you can effectively produce a current, an electron current that is very high, without any kind of space charge effect, because you have one electron after the other. Have you considered these numbers? What are the currents that you can produce?
Yeah, well, in the let's see. Most of these experiments are done in a regime where only a single electron is used. Okay, so basically, in order to prevent electron interactions, like Coulomb repulsion, for example, that will create big changes in the electron energy and momentum, and so that's how these experiments typically operate. There is also the other extreme, in which some experiments they have hundreds or thousands of electrons in each wave packet. Okay, and then they analyze the end result of that, and that's through very complex interactions. I haven't talked about that part. That's used a lot for diffraction, but also it could be used also to analyze optical excitations. You look at the diffraction that they produce on the electrons rather than the energy loss, right? So these other cleaner experiments in which you have a few electrons interacting simultaneously, etc. No, I think the way to get to that is by having multiple tips and multiple beams independent from each other, just aimed at the sample at the same time.
Yeah. Okay.
I think there is a question somewhere here.
Hello. Just oh, there is somebody. Yes. Gabriel asked whether it says, I have a question. Maybe my undergraduate physics is rusty, but I thought that a free electron couldn't absorb a free photon due to relativistic conservation of mass and energy. Is this right?
Yes. An electron cannot absorb a free electron cannot absorb a photon in free space because there is a kinematical mismatch of energy. You cannot conserve energy and momentum. This is for the same reason an electron cannot emit a photon spontaneously in free space. No, I mean you cannot think like one electron is moving in free space and if it absorbs a photon, it also can emit a photon. So now you are in the rest frame of the electron. How can this be possible? It emits a photon and then it recoils out of nothing. No? That's not possible. But so all of what we are talking here is with evanescent fields. So this is you are in free space. The electrons are free. They are not, in principle, they don't need to touch or to be scattered by material objects. They are moving through vacuum all the time, but they are interacting with fields that are not free. Okay, so the fields are not, the electrons are free, but the photons are evanescent photons in general. No? Photons that or photons that have components, momentum components outside the light cone, and therefore they have enough momentum to break the mismatch, this kinematic mismatch, right? And this happens, for example, in the case of this fin that I was mentioning. So here, yeah. So it's no longer a free photon; it's a photon that is reflected. So it's a semi-infinite plane wave of photon, right? And then so that explains why you can break this mismatch. Okay. Okay, that's it, no?
That's it. There's no more questions. If somebody else wants to ask.
Yeah, I'll be here during today and tomorrow. So
you will be here tomorrow. So if somebody wants to discuss this more in detail.
That's right.
Oh, okay. Okay. Thank you very much, Javier. See you.
Yeah. See you.